Optimizers and machine learning. What are they? One of the most fascinating ideas behind neural networks is their ability to learn, and this so-called learning is done by optimizers. In this video, we are going to look at how they work. To train a neural network, we have to have a labeled dataset, meaning that we have inputs and we know the answers for every data sample. Our task is to train a neural network so that it can perform well on unseen samples. When it is being trained, we show a neural network some inputs and let it make the predictions. Next, we compare those predictions with our actual labels or answers using a loss function. There are many loss functions, but the main idea is that the lower the loss function value is, the better our neural network is at predicting. So our goal is to minimize the loss. And this is the main job of the optimizer. The most well-known optimizer is called gradient descent. In reality, models have hundreds of thousands or millions of parameters. Large language models usually have billions. It turns out that the same optimizers can be used for training different tasks. But just to visualize how an optimizer works, let's say we have only two parameters. Different values of those parameters give us different loss function values. Knowing this, we can visualize it like a 3D plot, where x and y axes represent parameters and the z-axis is our loss function value. So this is a pretty simple function, but our task is to somehow find x and y values that give us the lowest possible z value. At the beginning we start with the random parameters, so let's say we start here. The question now is how to move this point down here. The idea is that we can compute the gradient of the loss function at this point with respect to both parameters x and y. This is usually done by deep learning libraries like PyTorch or TensorFlow. This tells us how steeply the loss function increases if we were to increase x or y. Next, we adjust x and y in the opposite direction of the gradient. The size of the step taken in this direction is controlled by a parameter known as the learning rate. So basically, we take our gradients, multiply them by a learning rate, and subtract the result from our parameters. And just like that, we are a little bit closer to our goal, which is a loss minimum. We repeat this step multiple times until we reach the desired value. Now, if the learning rate is set too large, we might overshoot the minimum. If it's too small, the training process might be too slow. And no matter where we start, we can see that gradient descent works with the different starting positions. It looks pretty easy right now, but keep in mind that we have a very easy loss function and only two parameters. What happens when we have a non-convex function, meaning that there are multiple local minimums and our goal is to reach the global one? Gradient descent might fail in this case, as it sometimes might get stuck in this local minimum. Of course, we can try multiple learning rates, but that does not guarantee we succeed. Luckily, there are different optimizers that can converge faster, are less sensitive to learning rate, and help us solve the problems with non-convex loss functions. In the following videos, we are going to explore gradient descent with momentum, AdaGrad, RMS-Prop, and Atom. So if you find this video useful, hit a like button and consider subscribing if you haven't already, and I'll see you in the next one.